Hello, I'm Mark Greiner from the Max Planck Institute of Chemical Energy Conversion. Today I'm going to speak to you about verifying experimental data. What exactly I mean by verifying, I will clarify in the presentation. To give you an overview of the presentation, I will start by reflecting on the information age. Then I will discuss how experimental science fits into the information age. I will discuss the value of FAIR, and I will conclude by describing some actions we are taking in verifying experimental data. Let's reflect back on the dawn of the information age. It began with Gutenberg's printing press in the 1440s. It was the first mechanized mass production of books. It cannot be overstated how important this revolution was. Prior to the printing press, books were copied by hand. A 500-page book would cost the modern-day equivalent of about 15,000 euro. This barrier limited the spread of knowledge to wealthy organizations. The printing press democratized knowledge and led to the scientific and industrial revolutions. The first mass-produced book was the Bible. It took 3 years to print 200 copies. At 4.1 megabytes for an ASCII-encoded Bible, this represents a data dissemination rate of about 270 megabytes per year. Contrast to today, the modern information age some 580 years later. Instead of Gutenberg's printing press, we mainly exchange information electronically using modern servers. Instead of 270 megabytes per year, we transfer globally some 2 zettabytes per year, and the rate is continually increasing. Information exchange is a major part of our daily lives and has revolutionized many fields such as business, technology development, and healthcare. However, in learning to deal with this enormous amount of information, we have come to an important realization that information is not the same as knowledge. Knowledge is actionable and is really what we are seeking. Consider this bit stream on the left. It contains information encoded into numbers. However, unless we can decode the information into something human readable, it is not very usable. Information can be used to generate knowledge, but transforming information to knowledge requires processing, metadata, and semantics. Without those things, information is no more useful than noise. Now, while that low-level example is somewhat obvious, consider a more high-level example. This statement is the ASCII-encoded characters from the bits in the previous slide. It's a statement I pulled from a Wikipedia page on eigenvectors. So, does this statement represent knowledge? Well, it depends. If the reader has an understanding of the entities that are referred to in the statement, then yes, it represents knowledge. But if the reader does not understand, nor have the possibility to learn more about the entities referred to in the statement, then it is no more useful to the reader than pure gibberish. This example shows that even human-readable, grammatically correct statements such as this one require context and links to other information before they become usable knowledge. The global information base continues to grow at a staggering rate. But this does not necessarily imply that humanity's knowledge base is growing at the same pace. Thankfully, there has been a lot of effort to turn this information base into a usable knowledge base, for example, with developments in search engine capabilities and with community-built resources. Now let's shift focus to the domain of physical sciences. The knowledge base here has roots some 350 years ago, with the first scientific journal published in 1665. Scientific findings were written in a manuscript, sent for peer review, and eventually printed in a periodical. Interestingly, the whole premise of the endeavor was to build a common body of knowledge. Now, some 350 years later, the scale of publishing has grown tremendously. We have over 28,000 journals publishing more than 1.8 million scientific articles per year. In each article, there are numerous claims, hypotheses, experimental methods, data processing routines, etc. Each one of these pieces of information, if taken in isolation, that is, without the context of previous works or precise descriptions of the work, would not be usable knowledge. Unfortunately, the original model of scientific publishing has not scaled well, and many problems have become embedded into the community. For example, there is very little standardization in many domains of the scientific community. There is also the reproducibility crisis. And lastly, scientific information in its typically published form is not suitable for big data applications due to the unstructured nature of the information. In recognition of these problems, a team in 2016 published the concept of FAIR, FAIR being an acronym for Findable, Accessible, Interoperable, and Reusable. They pointed out to the scientific community that all published scientific information should fulfill the criteria of FAIR, and in principle, if it does fulfill the criteria for FAIR, the information should be integrable into humanity's knowledge base. Now, this brings me to the notion of fairifying. By fairifying, I mean to provide all relevant data and metadata in digital forms and in a standardized way. While the findable and accessible parts of FAIR are doing pretty well with modern search engines and open access journals, the interoperable and reusable parts of FAIR are lagging far behind. The problem is the diversity of the information that needs to be documented. As an example, I will illustrate with a simplified experimental workflow. One might start with synthesis. An instance of a sample is synthesized by combining other materials, using some equipment by some user according to some method on some date. Then the sample is measured by some user using some instrument, having some settings, having been calibrated according to some protocol on some date to generate some raw data. Then this raw data is combined with other raw data, processed using some algorithms and methods to generate a figure, usually having a version associated with it. The processed data is then used to draw conclusions and hypotheses, summarized in written form in a manuscript, also associated with a version, then published in a journal and associated with some topic. In order to trace back all that has happened in a research project, you have to document all of these things. All of this data entry represents a substantial workflow overhead for the researcher. We can rightfully argue that a well-trained researcher should be documenting these things anyway, and while that may be true, researchers are not necessarily doing so digitally or according to a widely adopted standard. Researchers want to focus on their research, and therefore they optimize their documenting such that they can understand and analyze their data within the context of their research project. Their documentation is not likely to be meaningful in a global context, and in order to translate to a global context, a lot of manual work is involved. So what is the solution? How do we get experimental data and metadata digitized and in a standardized format that is both globally meaningful and using means that are compatible with the researcher's workflow? Well, there are a number of digital tools to help the researcher out. For example, there are laboratory information management systems. These are essentially databases for keeping track of various entities and processes, such as samples and calibrations. Then there is data acquisition control software. These are the interface between the researcher and the physical instrumentation. They are where the researcher defines instrument settings used to measure data, which is very important metadata for being able to interpret the raw data later. Then there are electronic lab notebooks, which are note-taking tools where researchers can document their observations and do on-the-fly analysis. This data is typically unstructured. In addition, there are tools like data processing software for analyzing data sets, word processing tools for composing summaries and manuscripts, and also version control software for keeping track of changes. There is not one tool that handles everything. In principle, in order to keep track of all information, these tools should work together in an automated way. But we are not there yet, and it requires a lot of change before we can get there. So we need to ask ourselves, if verifying experimental data requires so much, is it worth the effort? Should we change in this way? Do the benefits outweigh the costs? We need to think about this both on the strategic perspective of an organization as well as the perspective of an individual researcher. I can think of at least 3 very good reasons why we should change. One is knowledge retention. A second is that it can give rise to an easier workflow. And lastly, to prepare for the future. Let's consider knowledge retention. this is important both at the researcher and the organizational level. In research labs, employee turnover is inherently high, especially in university research labs, where most of the work is done by PhD students and postdocs with tenures between 1 and 5 years. The know-how of a particular research group needs to be taught to newcomers quickly, and the research team leader needs to do this over and over as students come and go. If the know-how is not passed on to the new generations, yet the young researchers are still expected to perform and publish progressive research, then problems occur, such as repeated errors in the published scientific literature. Here's an example from just this year, a review article written about how, after 50 years of research in photoemission spectroscopy, still a large majority of the community is not calibrating properly and publishing incorrect interpretations. What's ironic here is that we've known how to calibrate for several decades, yet this knowledge is not being transferred to new generations, and mistakes are being repeatedly published. The benefits of knowledge retention would be faster learning for new students, as well as less error published in the literature. The beneficiaries of this would be professors and research group leaders, students, as well as the general scientific community. And the benefits could be seen on the medium to long term. A second reason why verifying experimental data would be useful is that it can give rise to easier workflows. As instruments are becoming more automated, they generate data at a faster rate. This means that researchers need to be more efficient at managing and processing their data. The combination of software tools and standards would enable automated data organization. The beneficiaries of this change would be professors and group leaders as well as students. The benefits could be seen almost immediately. A researcher would just need to overcome the learning curve of the software used to do this. The third reason why verifying experimental data is valuable is that the future is fair. Consider that the digital world is providing new ways to innovate. Since the dawn of the Industrial Revolution, innovation was mostly done via closed innovation, meaning new knowledge was kept secret for a competitive advantage. The rationale behind this is when an organization invests in R&D and makes a discovery, they want to reap the rewards. While this certainly makes sense in a competitive free market, it can also give rise to innovation barriers. In the modern digital information age, the concept of open innovation is becoming more common. That is, spread knowledge and let the world innovate. The rationale here is that millions of distributed minds will be able to innovate faster. They will also come up with insights that a closed company culture could not see, and the results of the innovations will feed back into the know-how of the private companies. Companies such as Google are leading the way with examples such as their open-source machine learning library TensorFlow. Just to be clear, I do not mean to imply that all closed innovation will one day be replaced by open innovation. In a competitive market, it will probably always be important to keep some knowledge secret. However, the realm of open innovation will play a larger role even for private industry, and is certainly a good role model for publicly funded scientific research. So, if you are an experimentalist and you are new to the idea of digitizing and standardizing your metadata, you might be wondering where is a good place to start. Well, firstly, I don't think you need to go and enroll for a new degree in computer science. However, it's important to recognize that data management is no longer a thing that only computer scientists need to do. But in developing solutions that meet your requirements, you will likely need to describe your use case to computer scientists, in which case it is very useful to know a bit of informatics. I would recommend picking up some introductory high-level literature on information management, like this example here. This is an excellent resource I came across written by someone who has developed information management systems for researchers. Secondly, I think it's important to recognize that standards and patterns are very valuable. Without standards and patterns, it is very difficult to communicate information to other people. So get to know any standards that might exist for your particular domain. However, realize that a standard that is poorly built could do more harm than good. So it is important that whatever standards apply to your domain, they should fully meet your community's needs. so communicate with others in your domain and be proactive to define or revise the standards for your community's metadata. And lastly, I would say, if you've not yet done so, take the leap and start using an electronic lab notebook. There is a bit of a learning curve, and you may need to modify your workflow, but you will soon find many benefits in doing so. An initiative that FAIR-DI has put together is a proposal aimed at paving the way for verifying material science research. The consortium is called FAIRMAT, and in recognition of the wide diversity of use cases, it was realized that a top-down approach is likely to miss the mark. However, a bottom-up approach requires a lot of effort and proactivity from the end users. For this reason, FAIR-DI has brought together a team of vibrant experimentalists who are passionate about verifying experimental data and willing to do the legwork in paving the way for other experimental sciences. One sub-area of the project focuses on developing information management systems for several of the core experimental methods used in material science research. These tasks will be taken on by several university and government research labs across Germany. Among the deliverables of the project are the establishment of metadata schemas for several broad-reaching use cases, as well as integration of these schemas into software solutions. And to ensure that these efforts result in solutions that are widely applicable, they are being developed in cooperation with the broader community. As an example of how we are working with the community to build useful metadata schemas, I will describe a sub-project aimed at providing a crowdsourced database for electron spectroscopy. You can find out more information at spectroscopyhub.com. The idea is that we provide a service where users can post data publicly and receive a citable digital object identifier, or DOI. Through this effort, we will develop a standardized metadata schema for electron spectroscopy. This will also enable calibration tracking as well as instrument registry. Since one of the key objectives of these efforts is a metadata schema that meets the needs of the photomission community, this is one of the things that we have started with. And we've already published an initial version on GitHub. The schema is planned to go through several iterations as the service is tested with users. Here also is a demo of the user interface for the service. We aim at user value and user adoption, while at the same time acquiring rich experimental metadata and providing an easy and intuitive data entry experience. As you can imagine, easy usability and extensive metadata entry are difficult to balance. For example, one challenge we have faced is that one user's notion of a dataset can differ substantially from another user's notion of a dataset. What this means is that we must build in as much flexibility as we can, while not overwhelming the users with non-applicable entry fields. So, in summary, I hope I've convinced you that FAIR data has many important benefits, and that these benefits justify facing the challenges required for verifying experimental data. In order to make this happen, however, experimentalists need to be proactive to ensure that whatever solutions arise, their needs for data management are being met. One good starting point is to define your requirements with your community and get into contact with others such as the FAIRMAT team, who are actively working toward developing new solutions. I would like to thank you for your attention, as well as thank the organizers of this digital conference for making it happen. In addition, I would like to thank all of the people who support the activities of verifying data, especially Claudia Draxel, Matthias Scheffler, Robert Schlugel, and the entire FAIRMAT team.